All right. Hello, everyone. So in the last week, we started finally using more civilized words like force, and today we are going to make use of these of last week's knowledge. So we're going to start talking about weight and see how we can actually gain weight or lose weight. But what is weight? So let's start with that. If we put an object on scales, so these are the scales. The scales are on the ground. This is an object which we lay down on the scales. Now we know that there's a force, gravity force, F equals ma, F equals ma, right? So we know that this force here is mg. This object is still, it's not moving. So from F equals ma, let me move this a bit. F equals ma, object is still, so there is no acceleration. So if we now add all the forces on the system, we should get a zero because the object is not accelerating. We say there is another force. Remember Newton's laws, right? The object is applying a force on the scales are applying back a force which is equal in magnitude. So there's a force acting in that direction, which we can call the scale force, so Fs. And Fs is equal to mg. And that's why these are two vectors, if you add them together, you get F. Let me write this down completely. So you get F, S minus mg. This is the adding the two together equals 0. The object is not accelerating. So when we talk about weight, we really talk about what we see on the scales, and you need to be careful here because what you see on the scales is actually is not only the mass times the gravity, but as you're going to see soon, it depends on if the system is also accelerating or decelerating. The best thing to maybe to see this, if you think about an elevator, if the elevator is, if you've been in one of these elevators that can accelerate really, really fast, and imagine that you're going upwards, what do you feel? You feel that you're heavier, right? You are actually heavier for that few seconds that you're moving upwards because weight is not about the mass. Weight is what you read on these scales. So for these few seconds, you actually become heavier. Let's analyze this situation first. So this is the elevator, and the scales are still there. Remember, the weight is what we read on the scales, and we're standing here. And let's assume that this elevator now is accelerating upwards. So we have an acceleration in the upwards direction. Now, what you're going to see next is that you need to define, if you're already thinking about where is the y direction, the positive part of the y? Is it upwards? Is it downwards? How do we define it? You can define it the way that you would like to, but whenever we deal with acceleration in systems like this, I prefer to define it in the positive, in the direction of the acceleration. Okay, so in this case, I would define it positive in the upward direction. So this is y plus, right? Okay, so it's positive in vertically upwards. We do the same thing. We have mg. We have mg here. We have fs here. So now we can write, do we write fs minus mg or mg minus fs? We need to be careful. As I said, we define this plus. We are in the direction of the acceleration. So let's write fs minus mg. Now, this is not zero any longer because we are accelerating. So this is ma. F equals ma, Newton's second law. So what the scales would show us now, fs is equal to m times g plus a. The mass is the same. The mass doesn't change. The mass is the number of molecules that you have. They are the same. They're not changing. To be accurate, they are changing. But for this reason here, let's assume that these molecules are not changing. So this is the mass. The mass is constant. The acceleration now is not only due to gravity, but there's an additional acceleration due to the elevator being accelerating upwards. If the elevator was accelerating at 1 gravity, you would feel exactly twice the weight that you have. So these scales would give you twice the weight that you have. And you can see this here from the plus sign in A. If you put it this way, you have no problems with the signs. You see that there's a plus sign. It means that you are you're adding actually weight. Now let's do the opposite. In the opposite case, now we're accelerating downwards. Again, I want to choose my y positive in the direction of acceleration. I don't have to do that. This is convenient for me. So we have mg, and we have fs, the same as before. Now look at this. If I want to add the forces, then I have mg in the positive direction. I would write mg first. And now fs is in the opposite direction now to the y direction or the acceleration directions, minus fs. Again, f equals ma. So this is equal to ma. Now in this case, what you notice is that fs is equal to m times g minus a. Which means now if you're accelerating half the gravity downwards, you would actually feel you lose weight by exactly half. Now you immediately might think that, oh, what happens if A is exactly like G? This is a free fall. When A is accelerating with G, it means that, first of all, you don't want to be in that elevator. That means you're actually falling a free fall. And what you see here, let's write it down. So in case of free fall you would have is that Fs equals mg minus g equals 0. So you are weightless. In the free fall, you are weightless. In fact, you can try, I can't do this here, I don't want to do it also now, but you can try at home if you carry some books maybe. This is one of the useful ways of using books, is for physics. So if you carry them, if you're not reading them, at least you can make an experiment with them. So you carry them and you stand, or you need to be careful with that experiment. And then you stand on a table or on a chair and you jump. Just before you jump, you give it a little push just to make it a little, be a little bit away from your hand. And what you would feel is that all the way that you, in the jump, which is not a very long time, you would feel nothing. You would feel that there's nothing touching you. After you touch the floor, then you would feel also the hit. So it actually becomes a little bit heavier, and that's because of an impulse, which we might get to later on in the module. Okay, so in the case of free fall, the object is weightless. Let's do a similar analysis. We do the similar analysis for the case where you have an object and that object is hanged on a string. So this is the object. Now we know that we have mg here. We have tension in the string. We talked about tension last week. So we have tension in the string. Now, in a very similar way, let's just take the first case. In a very similar way, let me redo it here. This is the object. F equals ma. The object is now moving, so we know that the sum of all forces would have to be 0. So T minus mg equals to 0 in this case. So T equals mg. Well, if you travel a lot, one day if you will travel a lot, then you would actually use some kind of scales that is based on tension. It's quite handy. You can carry the suitcases with it, and then you can see immediately the weight. So in this case, T equals mg is the same as before. We had Fs equals mg. So this could also act as weight, scales. Now let's take the option where we are accelerating the whole system. So this whole thing is accelerating in the upper direction, and I don't want to write y plus again in that direction. Now you know the acceleration is in that direction, so this is the my positive direction. So now I can write, let me do it here, T minus mg equals ma. So we have T equals mg plus a. Just as we had before, here. Now we have T equals m times g plus a. The third case would be now if the whole system is accelerating downwards, So again, mg t. Now I write mg minus t equals ma. So now t equals mg minus a, just as before. All right, let's take a problem which is a little bit more interesting than this. Now let's take two objects. Let's take two objects. One object is hanged on this side, and another object is hanged on the other side. This is a frictionless spin. The two objects are hanged with the same string, so it goes around the frictionless spin. Okay. This is frictionless. And the strings are massless. Okay, right here, frictionless. Okay. This is M1, and this is M2. So we know that we have M1G here and M2G in that direction. And we know also that we have tension in the other direction. Should I write T1 and T2? No. I'll write just T. And we talked about the reason last time. Because if there would be T1 and T2, it means that there is a difference in the tension. Now think about Newton's second law. If you have difference in the tension, and if you take a very small part of that small element of that string, then you'd have a net force acting on that small element. But it's very small, which means that, and the force is finite. And the element is very small, which means that it would have an acceleration which is infinitely large. So it will break. So the tension has to be the same. Would these two objects have to accelerate or not? What do you think? But it depends on the masses, M1 and M2. Intuitively, if M1 and M2 are equal to each other, then there's no reason why this would start moving, right? But let's assume that M2 is larger than M1. So M2 is larger than M1. It's obvious that if M2 is larger than M1, then this would start accelerating downwards, and M1 would start accelerating upwards. So let's analyze this scenario, which means the whole thing would go around like this. This would go upwards, and this would go downwards. Should I write A1 and A2? No, it's the same acceleration. A1, oh, no, don't write A1 and A2. Okay, so you have A here and A there. It's the same acceleration. Now let's look at each of these objects separately. Let's start with object number 1. Object number 1 has mg and t, m1g and t, and the acceleration is in that direction. So I can write t minus m1g equals m1a. So t equals m1 a plus g, just as we had before. If we do the same for the second object, we have t here, we have m2g. Here, this is the first object, this is the second object. Now we have the direction of acceleration is in that direction. And remember what I said at the beginning, I always choose my direction in the direction of the acceleration. You can choose y being plus in one place and say, okay, I'm going to use that for both. That's completely fine. Just be consistent with that. Or you can choose it in this way, but you need to be careful. So the acceleration now is in that direction. This is the acceleration here. So we have t m2g minus t equals m2a. In other words, t equals m2 g minus a. So what you immediately can say about these two objects, and it's very intuitive actually, is that the object that is being pulled up would actually feel heavier, and the object that is being pulled down would feel lighter. If you think about it, you need to think about it, it should make sense because both of them are accelerating in the same rate. So this is for one, and this is for the other. So now we can find A. Acceleration would be m2 minus ma, divided by m2 plus, there is no ma, m2 plus m1, divided by m2 plus m1 times g. I had a feeling I said plus twice. This is minus and this is plus. Okay, so this is what we derived for the acceleration. As I said before, we're not going just to let go the derivation that we make. We want to analyze the derivations and make sure that things make sense as well. But before that, let's also find out what would be t. If you try to do this at home, and you should get the same things. What you need to do is have two equations with two unknowns. So if you take away this from this, you lose the t's, and then you get only the a's. And if you do the other, if you substitute a here or there, then you can get t. Okay, so please do this. I'm going to give you the final result, and we can spend the time in the analysis. Okay, so t would be 2 m1 m2 divided by m1 plus m2 times g. Now, automatically, whenever you derive any results, you want to check if the units make sense. And I see that the units make sense. Here I have kilograms, they cancel out. Here I have acceleration, here I have an acceleration. If the left side is an acceleration, then the right side has to be acceleration. Any term has to be with the same units as the other terms. The same thing here. We have, what do we have here? Yes, this is force. So we should have m times acceleration, right? Kilograms times acceleration. So we have t here. Let's see what we have here. 1m here cancels with the, so we have kilograms here cancels with the kilograms down there, and we end up with kilograms times the acceleration. So we're fine from the units perspective. Okay, let's analyze these equations. keep it here. Now, what happens when M2 equals M1 equals M? We say we expect that nothing would happen. A would be 0. If A is 0, if these are not moving, then the tension would be simply mg, right? Let's see if this is what we get. So the first case, when M2 equals M1 equals M, what we get really, M2 minus M1 gives us 0. So A equals 0, and T, let's see, we have M plus M2M, we lose the 2, we have M, we lose the M here, and we end up with mg. So T equals mg. What happens if M2 is much, much larger than M1? Let's think about it intuitively first. If M2 is much, much larger than M1, so this is so heavy that it doesn't even feel that that one exists, right? So what do you think will happen? This is so heavy and it doesn't feel about the other one. Well, if this object is very heavy and it doesn't feel the other one, there would be no tension in the there would be no tension here in the string. So basically, it would be falling in free fall. So M2 in this case should be falling in free fall. Let's see if this is what we get. So if M2 is much larger than M1, then this is neglected. This is neglected. So we have M2 over M2. That's 1. So A would be G. In this case, A equals to G. And T would be, what is T in this case? There is no T, right? M1 is much smaller than, so you take the limit where M1 goes to 0, for example. So T would be 0. Okay, what happens if we have the, which means no tension? There's no tension. What happens if we have the opposite scenario? M1 is much, much larger than M2. It's the same thing. You would expect that this would start accelerating in that direction. Now, here you need to be careful, because we assume that this is moving in the upper direction. So this tells me if this is now accelerating in the opposite direction, the acceleration of this object should be with a minus sign. Because remember, when we considered acceleration here, we took the acceleration in the upper direction. This is the type of analysis that you have to do whenever you make derivations, because you need to make sure that you you understand what you have. And many times I get some analysis in an exam for some silly reason sometimes, that the student maybe had some sign problem and so on, and they didn't get, everything went wrong, but because the analysis was good, they just got the whole marks. Okay, so it's very important that don't panic if you see that something is not right. Actually write it down, that you feel that the sign is not right, it doesn't make sense, the units don't make sense. At least that way I can understand that you understand what you have, that there's something wrong. Okay, now let's do this and see. When M1 is much larger than M2, so now this goes to 0, and we actually get A equals minus G. And this is exactly what we're analyzing now, what we expect. And T would, again, go to 0. There would be no tension. Let me give you another example where you could actually use reasoning. Of one of the things that they say that this object would have to gain weight, right? But this object would have to lose weight. Now keep this in mind. Let's take a numerical example. If the first object was 1.1 kilograms and the second object was 1.25 kilograms, okay, in this case, you say, okay, M1 is not much smaller than M2, so I cannot make the type of analysis that we had here. So I have to make some different analysis where, let's say, M2 is larger than M1, but they're both comparable. But you can't say much about the acceleration, apart from the fact that, well, this is the acceleration that you get. But you can say something about the tension. That you expect that the tension would be, this is for this case, that the tension would be, remember in this case here, it was mg, so it should be larger than m1g, but smaller than m2g. Now think about this. Now let's go back to the numerical example and see how this can help us. So we have 1.1, 1.25 for the second one. If you make the numerics, you should get A equals M2 minus M1. So we have 0.15. Divide by 2.35, right? M2 plus M1, 2.35 times G. So this gives you about 0.064 times G. This is times G, okay? It's not the gravity. Now, if you substitute this back into the if you want to find out the tension, for example, you can substitute back here immediately in one of these, or you can use this directly. Either way, let's say that what you got is the following: 3.5 G. Now you can be sure that you're wrong if you got this. Okay, this can't be true. And the reason is that T has to be between M1G and M2G, which means, you know, before you even start with the numerics here, you know that T has to be smaller than, what is it, 1.25 times G, and larger than 1.1 G. You know this. So any number that you get which is not in this range has to be wrong. Let me see if I have the number here. The number should be, you can check that, of 1.17. This is the correct solution. And you see that 1.17 G is between these two values. Okay. All right, so let's use what we have here and what we talked about previously. We had a uniform circular object Now with tension, so now we can also we can talk about forces. Before it was just a pull and a push. So we have this problem, and the object is a string here, and it goes around. And let's say that at one point it reaches here. So what I had with the water bucket. Now we can analyze the situation. This is omega. It's the angular velocity. Let's say this is point S, and this point here is point P. We want to analyze the different situations when it's at different points. The radius is given, that is R. And we need to define the positive y. I define it here as upwards. Let's start with this point first. When the object is at this point, when the object is here, we have mg, or we have t. This is all what we have. How many forces we have on this object? We have T, that's the tension, and the gravity. These are the forces that are acting on the object. But for the object to make this uniform circular motion, there has to be a centripetal acceleration. So there is a C here, centripetal acceleration. Otherwise, why would it change the velocity vector? Remember that? Okay, and I can write here AC is omega squared times R, which is also V squared divided by R. Okay, so at this point, so at point P, we start with, we have T minus mg equals, it's moving, right? That's the centripetal acceleration. So now we have T equals m times g plus AC. It's almost boring how much this looks familiar. Okay, this is what we had in the previous two examples, right? With the elevator and also with the string. It's the same type of problems, really. Okay, so this is what happens at point P. At point S, let's take now the color. Point S. Now we have mg in this direction, and we have t in this direction. So we go right, t. Now we can take the acceleration in the opposite direction. Okay, maybe I should have put this down here and this up here. It's in the same direction. So t plus mg now equals m AC. So what we see is that t equals m AC minus g. what happens at this point is that the object gains weight. At this point, the object loses weight. What happens when AC is exactly equal to G is that will give you 0, right? So there is no tension, first of all, and this is what you feel in your hand. There is no tension, but also the object is weightless, has no weight. So if you had a scale there with the object, this is the bucket of water. If you put scales here, and the object is there, or you can use the scale with the string, then it would show that it would be weightless. But it would be also a little bit dangerous to go to this acceleration, because what happens if you go a tiny bit below G? So if AC is smaller than G. So just to conclude first, when AC equals to G, the object has no weight, right? When AC is smaller than G, so the centripetal acceleration is smaller than G. How do you make the centripetal acceleration smaller than G? That's easy. All you do, you can make that omega smaller, or you can make the string shorter. If AC is smaller than G, we get tension smaller than 0. This is not physical. Okay, this is not physical. What it means by not physical is if that you have a bucket of water, and if you do that and you go to AC, which is smaller than G, you're gonna have a mess. Okay, this is the meaning of not physical. It won't actually make that turn. It would fall and it won't reach that turn. But the condition actually to have that turn is that you would have a centripetal acceleration. So if the AC is smaller than G, you don't have that condition fulfilled. So it won't make the turn. All right. That's it for talking about weight today. In the last few minutes, I'm going to talk about friction. Friction is going to be the next, the main thing I'm going to do in the next lecture, but I'm going to start with some introduction today because it's not a very simple subject. In fact, it can be very confusing. So let's start with what is friction. So far, when we considered objects, we assume that there is no friction. Right? So you push an object, and that object keeps on going forever. But now with friction, I can feel actually as I'm clearing the wall, you can maybe hear the sound also, right? I need to apply some force. It's not an incredibly large force that I'm applying to erase the wall. But if you have that object, and I want to make that object move, so I start pushing that object, okay? Just to show you this in this plane, I'm going to hold here for this not to fall. I'm going to start pushing. I'm pushing, but nothing is moving. The reason nothing is moving is that we can now think of the following. So there is a force. This is my force. I apply that force, but there's friction here, okay? Friction everywhere here. Okay, so I'm gonna put friction as being here. So this is friction force. Okay, now I start push more and more and more, and as I push, this friction force becomes larger and larger. I'm gonna put it here now so you can see it. So the more I push, the larger this friction force grows. So it's not something constant. So it keeps growing and growing and growing and growing, but it can't grow forever. I keep pushing until the moment that I actually am able to start moving the object. So there's a maximum, or there's a threshold for that, for the force that I need to apply in order for the object to start moving. This is just the first part of the complexity of the friction. Okay, so friction we have this object here. Now the surface, I'm not doing anything to the object. What is the friction force? 0. There is no force. Otherwise, this should start doing something. But now I apply force. This is my force. And as I apply, there would be some friction force, which is always opposite to the direction. So this is the friction force, Fs, or Ff for friction. Now, if we put all the forces on this system, we also have mg, and we also have the normal force. N equals mg, that's obvious. Nothing is moving in that direction. You can also put the coordinate system, x and y. It is a fact, it's an experimental fact that the maximum force, maximum friction force is proportional to the to n, to the normal force. So I can write mu as the coefficient. It has no dimensions. Right? This is force, and this is force. So this cannot have a dimension. So mu is the coefficient, the proportionality coefficient, right? That tells me what should be the, or what is the maximum friction force that we have on the system. If we know the normal force, you would know that friction force. In fact, if I go back to this problem, the more I push, the harder it would be for me to moving it. And this you can see here. So the maximum force that is needed is linearly proportional using this coefficient mu. This is all it says. So this is an experimental fact. Now comes the second part, which is not so intuitive, maybe. And that is you have two types of coefficients, two types of friction coefficient. One which is called ms, and the other one mus and mu k. So the first one is for static, which means that if I have this standing still and I just want it to start moving, And think about it in this way. If you have an object and you want to push that object, let's do it here. You have the object and you want to start pushing that object. Start pushing the object is not as easy as if the object is already moving or continue pushing it. Okay, so the first one, the first mu has to do with the object being still. And you want to know for example, when this object starts moving, so you're analyzing a problem where this is actually still. So you would use that mu. If the object, if someone tells you that the object is already moving and you need to analyze the system of an object which is already moving, then you use this mu k. So obviously mu s is always larger than mu k. Yeah, this when it make it start and this continue. All right. When objects, now with friction, things no longer move forever. If we go back to Newton's first law, we could understand that from the daily experiences that you're going to see this in a different experiment where we change the angles and then you can calculate actually at which angle this should be for this to start moving. But you can see that now this is not moving, right? But if I give it a push, it moves and after some time it stops. I can try to rotate it and it would stop. It doesn't even make one complete rotation. You can use other objects. So this is this circular example. Let's put it on the right. So you can make this move, so you have less friction there, so it can move for longer time, but eventually it would stop, right? So this is all nice and is quite intuitive. The question is, would you ever think that this would stop and suddenly start moving in the opposite direction? That wouldn't make much sense, right? It just stops and then that's it. You can try with something a little bit more complicated. If it works here, no, that was the wrong leg. Okay, so it goes around. It doesn't touch my finger good. It has friction there. There's also the friction from the air. And now it stopped. So it goes that way. You wouldn't think that it would actually start turning in the other way, right? Well, this could be a hint, actually. Let's see the next object. This is what you do on your board. You take spoons and you make art from these spoons. Now let's look at this. I'm going to turn it around. Oh, and it falls. I'm going to turn it around. Goes around. Stopped. Oh, it starts going back in the opposite direction. That doesn't make sense. I'm going to do it again. Oh, falls again. Falls again. It stops and starts going back in the opposite direction. Does that make sense? There's the high-tech version of my creation, which is this object here. See, it goes around, it stops, and then it goes back. So what's happening here? We would think that with friction, this object would just stop, and then that's it, right? What makes this object turn back? We're gonna get to that again next week. All right, thank you and see you next week. Bernard, are you there?
Yes, thank you.
All right.
So, hello everybody. I'll give you 5 minutes to go to the toilet or take some break, and I'll